Good afternoon, everyone, and thank you very much for this opportunity to present in this webinar. My name is Letizia CROCIATI, and I am a PhD student in the 847 program at the University of Bologna in Italy. Today, I am pleased to have this opportunity to share some of the results of my research, which focuses on bamboo joints. This project looks specifically at how we can design and test alternative connection systems for bamboo. And the main goal is to find solutions that ensure good structural performance while at the same time maintaining the environmental advantages of using a bio-based material like bamboo. In fact, we consider bamboo as a sustainable construction material, but the way that we join bamboo elements together, it's usually the weakest link in the system, both structurally and environmentally. So in this presentation, I will try to guide you through the context, methodology, the experiments I performed, and then the results and conclusions of this work. When it comes to actual construction, connections play a fundamental role, and differently from steel, concrete, or timber, bamboo is not a standardized material, and its geometry is irregular, its thickness and diameter may vary, and of course it has nodes along its length. Anyway, construction demands predictability. Buildings rely on standardized shapes and dimensions to ensure stability and safety. So this mismatch between the variability of bamboo and the need for regularity in construction is a fundamental challenge. And splicing and joining methods can help to overcome this. In fact, by joining shorter canes, we can create longer elements which reduce waste and can increase the efficiency of the whole construction system. But to do this effectively, we need joining systems that are both reliable and sustainable. Now, if we look at the literature, we can find some different classification of bamboo joints, usually based on the way forces are transferred. On one side, there are traditional methods, and this includes simple shaping techniques such as the so-called fish mouth cut of the cane, where the end of the cane is shaped to fit another element. These methods are clever and resourceful, but they are limited in terms of strength and consistency because of the material. On the other side, there are engineered systems, and these typically combine bamboo with materials like cement and steel. For example, by filling the cane with concrete or using steel clamps and bolts. And these solutions can provide very strong connections, but of course they undermine sustainability of bamboo because cement and steel are highly impactful materials in terms of carbon emissions. So here lies the challenge. Can we find a middle ground? Can we design joints that are strong enough for structural use but also environmentally compatible that the conventional solutions? So in this research, I try to address exactly this challenge. The system I propose is based on replacing cement and steel with bio-based or less impactful materials, which still keep the mechanical logic of an inner and outer reinforcement of this connection. So the system has two main parts: an inner core that transfers forces along the inner surface of the comb through the friction, and an outer wrap that provides radial compression by applying circumferential stresses. And instead of cement and steel, I used wooden dowels with softwood pine, glued into the bamboo cane with epoxy resin, and an external wrap made of burlap fibers. This combination was chosen to keep the joint lightweight, simpler to produce, and less impactful in terms of embodied carbon. So what I did during this research was to design the joint, build the samples, and of course testing them. And the key parameters I focused on were the diameter of the dowel and the wooden dowel and the anchoring length inside the cane. And these parameters were varied across all the specimens. For example, I tested 3 different dowel diameters, and for each one I looked at different anchoring length, 3 times diameter, 4 times diameter, and so on. And here the goal was to understand which factors really control the strength of the joint, and whether increasing bedman length or diameter could make significant difference. So now I'll be explaining how the samples were actually made. So it was used pound dowels, like I said before, glued into the bamboo combs with epoxy resin. Around the outside of the joint, it was added a wrap of burlap fibers, also impregnated with epoxy. So to improve the bonding, the surface preparation was really important. So the inner wall of the bamboo was brushed with a metal wire brush, and then the outer wall was sanded with sandpaper, and both were cleaned with acetone to remove dust and impurities. The resin was used for 2 purposes. The first, to glue the dowels inside the bamboo, and the second to impregnate the burlap fibers, making the outer wrap stiffer and able to transfer the stresses. In this way, the joint combined mechanical interlocking, adhesive bonding, and confinement for the wrap. So to evaluate the system, we decided to perform mechanical tests following the ISO standard for bamboo structures, which is the BS ISO 22157 of 2019. And it is important to mention that there is no official standard for testing bamboo joint yet. So the procedures that we used were adapted for those designed for bamboo culms. So we performed 2 types of tests. One was the compression test parallel to fibers, and the other one was the 4-point bending test. And this allowed us to see how the joint performed under the axial loading and under flexural loading, which are both very, very important for construction applications. So in the compression test, the bamboo segments were prepared with different lengths according to the anchorage depth of the dowel. So we tested a combination of 3 different dowels diameter and 3 different anchoring lengths. And the dowel was glued inside the cane, but a small portion was left outside of the comb, of the bamboo comb, so we could observe its behavior during loading. And here the main questions were, does the anchorage length really matter? Or is the diameter of the dowel the critical factor? And in parallel, we also performed 4-point bending tests. And here each specimen was 7 feet long with 2 bamboo segments spliced together using a dowel in the middle. And some joints also had the burlap wrap, while some other did not, so we could compare their behavior. And the canes were paired according to their diameter and density. This was made to reduce the variability as much as possible. So here the main questions was, does the burlap wrap improve the strength of the system, and how does the dowel size again influence the bending resistance? So looking at the outputs that we obtain, we can observe in both compression and bending tests that the failure mode was always due to the dowel. And this is a very interesting result, a very interesting outcome, because it tells us that the limit factor here was not the bamboo or the resin or the burlap, but it was the softwood dowel. So in a sense, the bamboo actually performed better than expected, but the weak link of the system was instead the element that we choose. So in the compression test, the failure was localized in the part of the dowel that was exceeding from the top of the cane, and the bamboo culm itself did not crash significantly. And what this means is that the strength of the specimen depends entirely, in this case, on the dowel's diameter, and the anchor length, which we thought might play a big role, actually did not influence the results. So this tells us that for compression, it is the cross-section of the dowel, if we choose to use softwood, that controls the performance. And basically, in the bending test, we saw the same trend. So the critical parameter was again the dowel diameter, and when the dowel failed, some of the bamboo canes started crack, because we also tried to notice after the failure of the sample what was going on if we keep going with the test. And what we also noticed was that the burlap wrap, unfortunately, did not significantly change this behavior. In fact, once the bamboo cracked, the burlap also failed in a brittle way right along the crack line. But it is also worth noting that many canes already had some small cracks before the tests, and this was because of the length that we need for the specimens, and this naturally influenced the results and shows one of the practical difficulties in working with bamboo. So to conclude, this study shows that the current joint design is limited to the choice of the dowel material. And if we want stronger joints, we should consider alternatives such as hardwood dowels or even engineered wood products, which could provide higher strength and reduce the risk of premature failure. And at the same time, the adhesive deserved further attention. In fact, epoxy works well, but has a very high environmental impact. And exploring more sustainable resins or bio-based adhesives could be a valuable direction for the future. Also, another potential improvement would be to machine the inner wall of the bamboo culm, and at the moment the inner diameter were vary significantly from one to another. And this variability complicates the selection of dowel sizes. While by machining the inner surface, we could reduce this variability, which would simplify the design and allow us to larger dowels, for example. And this could lead to a stronger joint and more standardized process overall. So yeah, here I've listed some of the main references that inform this work, and they range from classic studies on bamboo construction to more recent investigations on engineered bamboo joints. And they basically provide the theoretical background and comparison points that guided my research. And this is my contact information. And if anyone would like to discuss this topic further or perhaps explore possibilities for a collaboration, I would be very happy to continue this conversation after this webinar. And with this, I'd like to conclude my presentation. Thank you very much for your attention, and I look forward to your question if you have any.